Welcome to the next section in our video series on molecular modeling with WebMO and Gaussian. In the next few videos, we'll be talking about geometry optimization of molecules using Gaussian, how we use WebMO to build the input files that go into these optimizations, and the use of vibrational frequency calculations to identify the results of the optimization after they've been run by Gaussian. Before we get into an example of geometry optimization using Gaussian, it would be a good idea to ask the question, what is geometry optimization, and how do we use WebMO and Gaussian to take a molecule that we have created and convert it into an optimized structure? Although WebMO and Gaussian both perform what could be considered an optimization of a structure, they go about it in different ways, and here we'll focus more on how Gaussian actually performs the optimization rather than WebMO. WebMO's optimization is a much more coarse first-order pass that takes a structure and cleans it up before sending it to Gaussian. Gaussian, on the other hand, uses a successive optimization process where at each stage the geometry is modified by adjusting bond lengths, adjusting bond angles, and ultimately calculating the potential energy of that molecule. That potential energy is then compared to the previous geometry, and if it is lower, it is considered to be a more optimized state. At that point, the system moves into the next stage of optimization. On the graph, you can see that we have a point 0, which is the starting geometry. This is the original molecule that you will have created in WebMO. After this first optimization pass, the energy may have reduced to a point such as point 1. With successive optimization passes, the energy will reduce from point 1 down to point 2, point 3, and so on until it reaches point 6, which will be the point where no further energy reduction can be found by any change in the bond lengths, the bond angles, etc. This is considered to be the energy minima, and it is the optimized structure. This is the closest structure that Gaussian or WebMO can find to the real molecule geometry. Let's look at an example of how to do a geometry optimization on a molecule that you're probably familiar with now, carbon dioxide. We've created a new project in WebMO, and we're going to go to the periodic table, and we're going to start by adding a carbon. Next, we go back to the periodic table, and we're going to add a couple of oxygens, and I'm not going to be overly careful about where these go, just to show you an example of how well Gaussian and WebMO can do an optimization. We return to the left, we click on the build button, and we're going to add bonds between these by clicking on the oxygen, dragging to the carbon, or by clicking on the carbon and dragging to the oxygen. At this point, it's not terribly important which direction you go as long as you click and drag on the proper atoms. We do the same thing on the other side, and now we have something that looks almost like a very bent carbon dioxide. We can click on the rotate button and we can see that this is a bent structure. We can click on the adjust button and we can select one of the oxygens in the carbon to find that it is a very long bond length. We can select the other oxygen to find out that our bond angle is just short of 160 degrees. Now, all of the atoms are there and all of the bonds are there, but we can tell that based on the angles and the bond lengths, this is not a real carbon dioxide molecule. And if we were to pass this into Gaussian, Gaussian would have a harder time dealing with it than it would if it got a real carbon dioxide molecule. What we want to do is we want to start by doing an initial optimization pass in WebMO. This is done by going to the cleanup menu and selecting a comprehensive mechanics optimization. What we can see from this optimization is that the bond lengths are now much shorter, and the angle between the oxygens and the carbon is now approximately 180 degrees. Or if we want to check that, we go back to adjust, we click 1, 2, 3, and find out that the bond angle is actually exactly 180 degrees, and the distance between one of the oxygens and one of the carbon is 1.3 angstroms. This is a lot closer to reality than the 2 we were getting before, but it's still not quite there. The next step is going to be sending this to a Gaussian optimization, which is the more fine, more accurate optimization technique, which of course uses more computing power, which is why we wanted to do the rough optimization first. The way that we send this to Gaussian, as with the last example, is we click on the continue arrow at the bottom. This opens up the Gaussian job options window. In the next video, we'll be talking about how we can set these job options and pass this input structure into Gaussian, as well as what the results that we get from Gaussian mean, and how we can use vibrational frequency analysis to test that the results we are getting actually represent something found in nature.